So, they tell us here that the arc over here is 240. Is it okay?
Yeah.
If that arc is 240, what is the arc that we're interested with, the yellow segment? 120. Okay? So we need that 120 written out here. And the reason that 120 is useful to us is obviously it's going to help us find the area of everything that is yellow right now, right? Okay. So how do I find that area?
1/2 base on size.
No. Everything that's yellow.
Everything. I thought you were talking about the triangle. Can you let me answer? Because I don't know if I actually does. The angle.
Okay.
Over 360. Yeah.
Okay. So there's our formula for finding the area of everything that's yellow. Okay. So x in this case is 120, right? We have 360, and then pi. What is r squared going to be? 9. What's 120 over 360? What's that going to reduce to?
What? Yeah, 1/3.
1/3. So I have 1/3 times pi times 9. What's 1/3 times 9? 3. So it's going to give me 3 pi. It'd be meters squared as my area of everything that's yellow, right? Okay. Now what we have to do is find the area of the triangle. Okay. So area of your triangle. What's the area formula for a triangle?
1/2 base times height.
1/2 base times height. So we need to figure out what B and H are for that triangle right there. Okay. So this is where it's important to understand the relationship between that arc and this angle. What is that angle right there? 120. Okay. Now, every triangle has 3 altitudes. Okay. One of the altitudes for this triangle is out here. The other one is down here somewhere. We have absolutely no idea about what those lengths are because we have no idea how they relate to other objects in this picture. This is a 3rd altitude. That one, we know a lot about how it relates to other objects here. Okay? We don't know its length yet, but because we know that it relates to an isosceles triangle, it is the altitude that is drawn from the vertex angle of an isosceles triangle to the base of the isosceles triangle, because obviously the whole white triangle is isosceles, right? Everything, both sides are both 3, right? Okay. We know that makes it perpendicular down here. And what does that do to that and that? Makes them what? Makes them congruent. Okay. We also know that it does something to this angle right here. What does it do to that angle right there? Bisecting. You told me that angle was what to begin with? 120. So if I bisect it, I get 60. And now that relationship gives me a 30, 60, 90. Now we have information. Let's go about finding information about this 30, 60, 90 triangle. Okay? Because if I can find out the altitude of that, is that the same altitude as the whole isosceles triangle, right? And then this distance here is the base of that triangle. What would I do with that to get the base of the triangle I'm actually trying to find the area? I would double it. Okay? So, we know that this is across from 90 degrees, right? So what side is that for any 30, 60, 90 triangle? 2n. Okay? So n is going to be what?
3 halves.
3 halves. And that goes across from what angle?
30.
30. So this distance right here is 3 halves. That is h. That is h for your triangle formula. Does that make sense? Okay. If that's 3 halves, what is the segment across from 60 going to be? Okay. And n is 3 over 2, right? So that segment is going to be 3 halves times radical 3. What then will be that distance? 3 radical 3. It'd be twice that, right? I double that. If I were to double that, don't the 2's cancel? Leaves me 3 radical 3. So B is 3 radical 3. So what I've got, guys, is information to find the area of that triangle. We know this chord is 3 radical 3 units long, and that distance right there is 3/2, and that's your B and your H, right? So I go 1/2, B as 3 radical 3 over 1, and H as 3/2. What do I get when I multiply straight across? 9 radical 3. And what do I get when I multiply straight across the bottom? 4. There's the area of the triangle. What do I do with these two numbers to find the area of the yellow? Subtracting. So, which one's bigger? 3 pi. So we have 3 pi minus 9 radical 3 over 4. And that is the area, the exact area of that yellow region. Okay. When they tell you, so the directions will kind of maybe shed light on this a little bit. They'll say, leave your answer in simplest radical form. That's what we have right there. When they do that, they're kind of expressing to you that you should be using special right triangle somewhere throughout the problem. Okay. They like to give that arc to be 120. They like you sometimes to work with this being 60. So if that was 60, what would that angle there be? 30. And this would be 60 then. And we end up with the same type of problem, right? Yeah. So they like to give you this arc out here to be 60 or 120. Okay? Now, and because taking half of that thing gives me a special right triangle on the inside. They can give me 90. Okay? And I think I've got one here with 90 in it. We did one of these yesterday. That's not it. Not it. I must have deleted it. I'll get back to it. All right, so looking at this one. Let's say, so we know that this angle is 90, so my arc is 90 up here. Okay. Let's say that this is 6. I'm making that 6, right? If I want to find the area of that red segment, okay, we're going to first find the area of the sector, right? So area of sector, x over 360 times pi r squared, right? Yeah. What's x in this case? 90. 90 over 360 reduces to what? 1/4. Times pi times r squared would be 36, correct? What's a fourth of 36? 9 pi. Okay, so that's something we can do. Okay, my hopes are that you realize that the sector, even though that's the new thing, that's not the hardest part about these questions. I think the hardest part about these questions is finding the area of the triangle. Okay, if I want to find the area of this triangle, you can go through what we did in the last example. But my hope is that when we're doing intermediate steps, okay, for new problems, is that we realize that just because it's similar to other problems or the same type of problem doesn't mean that that's always going to elicit the exact same steps. And my fear is that we're going to go through this using what we learned in the last one and address this one and waste a bunch of time. Okay? What kind of triangle is that blue triangle? The right isosceles triangle. The key thing here in regard to finding the area is that it's right. Okay? The area of a triangle is 1/2 BH, right? 1/2 BH. In a right triangle, isn't this segment here an altitude? And isn't this segment here an altitude? Yeah, we've talked about how in a right triangle, the legs of the right triangle are both altitudes. So if one of those is an altitude, let's choose that one to be an altitude, then the base is defined as the segment that the altitude is perpendicular to, right? Isn't that altitude that we just chose perpendicular to this segment here? So it makes this 6 here the base. Does that make sense, everybody? So finding that area, 1/2 6 times 6, well, that's 18, isn't it? And now if I want to find the area of the red segment, it's simply 9 pi minus 18. And that's much quicker than the alternative approach. I'll do the alternative approach with you, but it's not, my hopes are that you realize here that it's not really friendly. Okay, it incorporates all the algebra and geometry that we kind of want to avoid. All right, so if I do that, now that's the H that we talked about in the last problem, right? That's H in the last problem. When I draw that in here, what does it do to this 90 degrees down here? What's that angle going to be right there?
45.
45. Okay. Do we now have a 45, 45, 90 right triangle right here?
Yeah.
Okay. So if that's 45, 45, 90, this was, I erased it, but we said that this was 6, right? Isn't that my n radical 2 side? Okay, so we go through the algebra. It says n would be 6 divided by root 2. Well, isn't this side here n for my 45, 45, 90? So that height, the altitude, should be 6 over root 2. If this is a 45, 45, 90 triangle, isn't this also 6 over root 2? Okay. Then to find the base, my goal is ultimately to find the area of everything that's yellow, right? So what would, if this distance here is 6 over root 2, eventually, I'm going to keep it there now because the intermediate algebra doesn't require us to rationalize. It's the answer that we want to rationalize. So I always keep it in. But if this little section here is 6 over root 2, what's this little section? 6 over root 2. What's 6 over root 2 plus 6 over root 2? 12 over root 2, right? So as we work through that, we find that this altitude right here is 6 over root 2, so that's H. And this distance right here, which is B, is 12 over root 2. Does that make sense? Now, answering Trey's question about don't I want to get that root 2 out of the denominator, that's only a presentation thing when I'm done and I want to present my answer. Does that make sense? I don't want to present my answer with radicals in the bottom. When I develop radicals throughout all the algebra that I have to deal with on a regular basis or on a yearly basis with teaching high school, I always want to rationalize at the latest possible step because things like what are about to happen here might occur eventually. If I multiply straight across here, what's 1 times 12 times 6? 72. 1 times 12 times 6 is 72. Now when I multiply the bottom, let's just do the radical part first. Let's radical 2 times radical 2. Radical 4, which is 2, and then you multiply by the other 2 that's out here in the 1/2, right? So it gives me 4. So do you see there that the radicals dissolve themselves in the next operation? Okay, where if I could have done it here, I could have rationalized them there, but it would have given me 3 radical 2 over 2. So I still have radical, and it would dissolve itself down here eventually anyways. But if I did that, I'd be wasting time. Does that make sense? Okay. So and you guys don't know what's going to happen. A lot of times when I work through a problem for the first time, I don't know if that's going to happen. So that's why I always leave them unrationalized in the hopes that they are going to kind of take care of themselves. And if they don't, if I'm left with an answer at the end that does have a radical in the bottom, then I rationalize that. Does that make sense? Always do that process kind of as late as possible with the problem, and you're going to save yourself some effort, some time. So that obviously is another way to get that 18, right? Would you agree that doing it in blue was much quicker? And that's what I'm hoping you see here, is that when you're seeing a problem like this, even though it's the same exact setup as the last one, exact same picture, still asking us for the segment area. My hopes are you look at the components that are provided and say, okay, they're giving me things here that allow me to do the process a little bit easier. If I don't recognize that, I go through that radical work and I waste time. Okay, now you do get better radicals there, but you're not as efficient as we maybe like to be. Yeah.
If your first angle isn't 90 degrees, don't you have to do it that way?
Yes. So this is a special scenario, a special case that we can do this blue stuff here because this angle here is 90. Okay, or that arc is 90. If it gives me basically a right triangle in here, right? If it was any of these other ones, so if it was this one where that's 120, then I have to use that longer process. If we do this one here, and this is the one that I really want to get to, because I think with our homework, and we see it a lot, and they do it. You hear me say they do this on purpose. They give you a lot of measurements based off of like Math Excel knowing that this process needs to be done or this relationship needs to be used, and it's going to create 30, 60, 90 triangles with the numbers that they give you. Then every once in a while they'll throw one in like this, and we go blank because we've trained ourselves to work with 30, 60, 90s and that kind of thing, and then we forget that there is a template, there is a process for doing this when you don't have a 30, 60, 90 triangle, okay, or a 45, 90 triangle. And that template that is going to address this is ultimately that. So Katoa, when this angle down here, this arc, is not a multiple of 60 or a multiple of 90 or something like that, we have to use SOHCAHTOA, okay, your sine, cosine, tangent functions. Okay, so finding the area of the sector here. Still x over 360 times pi r squared. A lot of times, and people are coming to me today during walkout time, which is awesome, with these questions, when they don't give me 60 or 90 or 120 or something like that, this is going to be kind of usually a nasty fraction. And if you look at this one, so 50 over 360 times pi times r squared would be 81. Well, 50 over 360, that reduces to 5 over 36. That's as nice as that fraction gets. Okay? It's kind of ugly. If I multiply that by 81 pi, okay, so 5 times 81 is 405, and then 36 times 1 is 36. Now that's ugly, but that still goes down a little bit. Both those numbers are divisible by 9. So I'll have 45 pi over 4. Not as nice and clean as a number when it gives me to start off with a 60 degree or a 120 or a 240 degree angle. Does that make sense? But it's still the same process. So 45 pi over 4 is now the area of the sector. Okay? And that's that slice of the circle. Okay? Now we got to find the area of the triangle. And this is where I think with a lot of these questions, I think this is question 10 in the homework that people were coming into an issue with. I got to find 1/2 BH. Okay? So we always draw down that altitude on the interior perpendicular to the chord down here. Okay? What would this angle right here be? 25. Okay, so that angle is 25 degrees. This is 9, right? If I want to find H, and this is something that I don't think enough people realize or see, or even do if they do realize it, and it creates sometimes a problem. If I were to give you this picture just like this, is that a problem that maybe we can do from chapter 7? If I ask you to find H? Okay. So when that happens, and I see some people doing this on their work when they bring it to me, it's really not always organized, but they have this little triangle drawn somewhere. Because now they say, well, H is what side compared to 25? The adjacent side, right? 9 is the what? Hypotenuse. So which trig ratio then uses adjacent and hypotenuse? Cosine. So I'm going to say cosine of 25 is equal to h over 9, multiply both sides by 9, and it gives me that to be h, right? Okay. So that's the h that's going to go in my formula here. Now I got to find b. Well, I'm finding b, I'm just going to call this distance here x. Let's say I want to find that. What would x be in relation to this 25? Opposite. And this is hypotenuse. So now what uses opposite and hypotenuse? Sine. So I'm going to write sine of 25 is equal to x over 9. So then that's going to give me 9 sine of 25 is equal to x, right? Now at this stage, I'm going to unhide. Right. Yep. So x was just this distance right here, correct? Remember, I'm trying to find the area of that entire triangle. So what do I need to do with that x to find this entire bottom here, this entire base? Multiply it by 2. So what's 9 times 2 going to give me? 18. So the b value then for my formula here, b would be 18 sine of 25. Now you've got the components that need to be plugged into this formula. I'm going to write that up here real quick. 1/2, and this is the way I would type it into Desmos or your TI-83, 84, or if you've got one of those TI-30s or whatever. I go 1/2, 99 cosine 25 times 18 sine 25, and that's going to be your area of your triangle. Is that okay? So let's see what this looks like. Get Desmos open here if I can find it. As we do problems like this, guys, think about the angles that just in real life show up more often. Do you have an angle of 60, 120, 240, 90, or 270? So you got 5 angles there versus all the other angles between 0 and 360. You see how all the other angles, like 50 degrees, 40 degrees, 28 degrees, 36 degrees, 118 degrees. You see how there's more of those than there are the special triangle angles of 30, 60, 90? Does that make sense? So in regards to the amount of problems that incorporate this process right here with the 9 cosine 20 and the 18 sine 25, that is more common than dealing with dealing with special right triangles, okay? Because there are more angles of the nature of 50, 51, 52, 53 versus 60, 120, 240, and so forth. Yeah? How did I get to 18? Because so to find the area of that blue triangle, I first need to figure out what that x is, right? Okay? And that's going to use the sine. So that's the sine of 25 is equal to x over 9. So that ended up giving me 9 sine of 25. And that would give me that x right there. But remembering that we want to actually find the area of that entire white triangle, right? So this base here is actually double this. So I take 2 times 9 sine of 25, and that is that base right there. So 2 times 9 is where that 18 comes from. So if we type this in the Desmos. And when you have these angles that are 50 degrees, 30 degrees, that kind of thing, where you're not getting, and I say 30 because that angle cut in half would be 15 then. So 50, 30, 40, 25, 26, when these are non-special right triangle numbers, okay, they're usually going to ask you to write your answer as a decimal. Okay? If they wanted an exact answer, this is what you would type. This is what you would write as an exact answer. We had 45 pi over 4, and then it was minus. We had 9 cosine of 25, and then 18 sine of 25. Now I know I'm in the wrong mode here with my calculator. I want degrees. Okay, did I have the right 9 sine, 9 cosine 25? I mean, this should be a positive number, right? So I've got something going on here. Oh, I forgot my 1/2, right? So 1/2 base times height, right? Does that make sense? So I can type that all in my calculator just like that, and it gives me back my 44.3, and I can round that to whatever decimal I need to. If they were to ask you to leave this as an exact answer, which they're not going to do with sine and cosine, you could, though. You could take, what's half of 18? 9. So those two things give me 9. Multiply by this 9 gives me 81, right? So if I wanted to, so then we'd have cosine 25, sine 25, and you see it gives me the same thing. So I could multiply those rational numbers together. Show you something that maybe you'll recognize in a couple years. I think it's always important to kind of visualize where we're going with this stuff. We could actually write this as minus, okay, so that's going to be 81 over 2, so let's write it as 81 over 2, and now I can write sine of 50. See how that gives me the same answer? Okay, and it's a little bit more condensed, a little bit more concise than maybe the one above it, because now I'm only using the sine function instead of the cosine function. So those are trig relationships that we learned in 11th and 12th grade that we'll use. Okay, we got a little bit of time here, so let's talk about.
Oh, I have a periodic table on my calculator.
Huh?
I have a periodic table on my calculator.
That's awesome, man. That's fantastic.
I know. Games online. I don't know. I'll look at how it games.
Do you guys remember? Do you guys remember a rule that we could use to find this length right here? I'm just looking at the triangle here. Do you remember how to find that length? Do you remember this formula? Well, let's call this B. Do you remember B squared is equal to A squared plus C squared minus 2 AC cosine of capital B? Remember the law of cosine? We could do that. I want to see if we get the same answer here. If I go B squared, A squared plus A squared, what's A squared going to be? 81. C squared is going to be 81, so that's 162, right? Minus 2 times A times C, well, that's another 162, isn't it? Cosine then of 50. Okay, so that right there is the same thing as B. We said H was 9 cosine of 25, right? We still have to use the right triangle stuff to find H. But let's go back to Desmos and type that in. So I'd go, and let's just make the comparison of what these two triangles areas would be. So that was the area of the triangle, kind of using the longer approach. This would be the area of the triangle. We go 1/2 base. We just said the base now was 162 minus 162 cosine of 50. And then the height was 9 sine of 25. Or not sine, it's cosine 25, sorry. Cosine 25. And that's, oh. So this is b squared. What did I need to do to that if that's b squared? I need to square root it. So let's put, now this is something you'll learn later. It's just because I messed up. I'm going to raise it to the 0.5 power. That's the same thing as taking the square root. Does that give me the same area then? Okay. So that's the benefit of knowing other relations. That's the benefit of knowing that I can use the law of cosine inside there to find a dimension instead of maybe breaking it up into two right triangles and finding dimensions that way. I think using the law of cosine is faster, but it's because I know and I force myself to work with that in other areas that it's as easy to me as like a squared plus b squared equals c squared, right? To you, it's not that, because I've been using it since I was your age. You've been using it for, maybe 3 weeks, and it's been a long time to use it, right? So the exposure that you have to it, the exposure that you force upon yourself in regards to these things, are going to allow you in upcoming questions, problems, courses, to alleviate some of the work if you know these additional relationships. Does that make sense? Okay. I'll do that right now for you guys. I'm going to extend that assignment, okay, for one more day, and I'll put 2 similar exercises on. So if you struggled, if your person says, I worked on it, I got it done, I got 70% on it. So you go back through it with this instruction, and now you can get 100 on it, right?
I got like an 80.
Okay. So my hope is that we go back and fix the ones we missed.